We just covered some cations and anions and the ionic charges and why they would be ionic charges and how they want to be a noble gas. And we know that group 18 elements are also called noble gases. We've covered that, and they're chemically very unreactive. Okay, they have a full outer shell. They're happy. They're noble. They look good. They feel good, and they don't want to react with anything. Okay, because if they react with something, that means they have to lose their um, their full valence orbital. Okay, whether it's eight electrons or whatever it might be. Okay, and all atoms, when they're neutrally charged, they want to lose those electrons or gain the electrons so that they can fill up that valence shell. Okay, this is basically because, again, the noble gases have a full valence shell. Okay, and in grade 11 and 12, you'll probably learn of some and how these noble gases react with each other or react with other elements. But for now, just know that full valence shell means that noble gases are very unreactive. Okay, and all atoms are trying to get to that full valence shell configuration by either gaining electrons or losing electrons. Okay, becoming negative or positive. So all other elements, again, react chemically in an effort to acquire a full valence shell. And there are a number of ways that we can do this, right? An atom can acquire a full valence shell in one of the three ways. It can give up electrons to form a cation, so now you have more protons and more electrons, such as sodium. It can gain electrons to form an anion, such as chlorine. Okay, so it just takes one electron, saying, "Yo, I want that electron," takes the electron and holds on. Now you have more electrons than protons, and it forms an anion. Or it can share electrons, and we'll talk about sharing electrons later on. This could be such as gas or chlorine gas or something like that. Okay, so the first way that we're going to discuss on how elements actually gain that valence and gain that are able to create that full valence shell is through ionic compounds. Okay, ionic compounds are compounds that actually use cations and anions, okay, and they are attracted to each other. Okay, so the cations say, "Hey, anion, you want my electron? Take my electron." And the anion's like, "Yo, yeah, I want your electron," so it takes your electron. It takes that cation electron. So cations are positively charged, and they're attracted to the anions, which are negatively charged. Okay, the attraction between the oppositely charged ions is called an ionic compound, and this bond is again very, very, very strong. Okay, it occurs due to a transfer of electrons. So you have your sodium here, you have your fluorine here. Okay, we know that sodium and fluorine, okay, sodium wants to get rid of one electron because in its outer valence shell, it has that one electron. And fluorine right here wants to gain that electron, okay, because it has seven electrons in its valence shell. So sodium says, "Yo, take my electron." So fluorine takes their electron, and now we have a positively charged sodium and a negatively charged fluorine, and they're attracted to each other based on positive and negative attraction laws, right? So now you have the positively charged sodium and the negatively charged fluorine, and they're attracted to each other. Okay, so substances composed of cations and anions are called ionic compounds. So sodium fluoride, okay, is an ionic compound. And remember how I said in the last lesson that any anion any anion has the IED ending, okay, so that we can call it now sodium fluoride. Okay, most ionic compounds involve bonds between metals and nonmetals. Okay, metals and nonmetals. Why do you think that is? Why do we think that metals and nonmetals are the ones that create the ionic compounds? Think about the ionic compound. It's the attraction of positively charged and negatively charged uh, ions that come together. So we know that metals in group 1 and group 2, okay, and group 13, they are all positively charged. We know that nonmetals in group 7, 6, and 5, they will become ionically charged, negatively ionically charged. Positive and negative react, okay, so they come together and they form ionic compounds. And that's why most ionic compounds involve metals and nonmetals. okay, because that positive and negative attraction that they have together. There are some forms where we have anions as polyatomic ions, but we'll talk about that later on in this unit. But for right now, just know that nonmetals and metals form ionic compounds most of the time, okay, for that positive and negative attraction. So we know that metals, the sodiums, the calciums, the magnesiums, metals in the, in group 1, group 2, group 13, okay, they want to lose electrons and nonmetals, okay, or they want to lose electrons. And we know that nonmetals, such as your chlorine, your fluorine, your, uh, your, um, your chlorine, your fluorine, your sulfur, your oxygen, they want to gain electrons. They're like, give me the electrons. I want to fill my valence shell. Where the metals are like, yo, take my electrons. I don't want my electrons. I want to look like a noble gas. Okay, so because of that dynamic, because they have metals lose electrons and nonmetals gain electrons, we can predict the chemical formula of an ionic compound using the number of valence electrons. Okay, so right here I have lithium and oxygen, magnesium, sulfur, aluminum and chlorine, and calcium and phosphorus. Okay, I'm just going to go to this little slide right here. Um, let's move this so it's straight. Right here. Okay, so we have lithium and oxygen. How many electrons in the valence shell, or how many valence electrons does lithium have? Okay, well, I got my periodic table right here. Okay, I find lithium. Where can I find lithium? Lithium, lithium, lithium. Oh, there's lithium. Okay, lithium is in group 1, so we know that it has one valence electron. So we can go here and write lithium will become positive 1. Okay, lithium wants to lose an electron, so a lithium ion will have a positive 1 charge. Okay, we go back to the periodic table, and I try to find oxygen. Where's oxygen, 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 oxygen? Right here, number 8. So we got 1, 2. It's in group 16, so it only has how many electrons in its outer shell? 6 electrons in its outer shell. Okay, so I'm going to just jump over here again. Oops, sorry, wrong slide. Okay, and we know that oxygen wants to gain 2 electrons. So oxygen is going to be -2. Okay, lithium wants to get rid of an electron, so that means it's going to have more protons, making it a positive charge. And oxygen has 6 valence electrons, and it wants to gain 2 electrons. Okay, and because it wants to gain 2 electrons, it's going to be negatively charged because there's more electrons than protons. Okay, and we can use a method called the crossover method. Okay, the crossover method is now I see my charges here. I have one charge right here, +1 on lithium and a -2 on oxygen, and I literally just cross them down this way to form my equation. So it's going to take 2 lithium ions to bind to my 1 oxygen. And that's how we can predict our chemical equation, our chemical formula, using valence electrons. Now let's look at magnesium and sulfur. Okay, so magnesium and sulfur. We can see, magnesium and sulfur. Okay, let's look at magnesium and sulfur right here. I'm going to go back to my periodic table, so it's going to shift screens here. Oops. So I'm back here at my periodic table, okay, and I'm looking for magnesium. I see magnesium's in group 2. Okay, group 2 therefore will have how many valence electrons? It has 2 valence electrons. Okay, so I'm going to go back to here and I'm going to write Mg, and it wants to get rid of 2 electrons, meaning it's going to have 2 more protons, so it's going to be +2. Okay, and then I'm going back to my periodic table, which will be right here, okay, and I am looking for magnesium sulfur, okay, and sulfur again is in group 16. Group 16 has how many valence electrons? Okay, so if this one has 8 valence electrons, noble gas, this has 7 valence electrons, my halogens, okay, this 16 is going to have 6 valence electrons. My sulfur has 6 valence electrons. How many electrons does sulfur need to reach noble gas argon? Well, it needs two electrons. And if it gains two electrons, that means it has two electrons more than it has protons, meaning it's going to be a -2 charge. Okay, so then I'm going to have my sulfur with a -2. Okay, and I can do my crossover method. Okay, and it's 2 to 2. And because it's an ionic compound, the ratio, you're looking at the ratio, you're not looking at the total number. Okay, so we know for every one magnesium ion, you're going to have one sulfur ion. Okay, so you're going to go magnesium, sulfur. Okay, magnesium sulfide, lithium oxide. How about aluminum chlorine, not chlorine, chlorine. Okay, so I'm going to go back to my periodic table. Right here, my periodic table, and I'm going to look for my aluminum. Where is aluminum? Aluminum, group 13. Okay, so if group 1 has one electron in its outer shell, group 2 has two electrons in its outer shell, and its valence shell. Group 13, we're going to skip the transition metals right now. Okay, group 13 will have three electrons in its outer shell. Now, is it easier for aluminum to gain 5 electrons or lose 3 electrons? Okay, it's easier for aluminum to lose 3 electrons. So if aluminum loses 3 electrons, okay, it's going to have how many more protons now? Yeah, it's going to have +3 because it's going to have 3 more protons than it does electrons if it loses 3 electrons. How about chlorine? So let's go back to my periodic table. Chlorine, okay, chlorine's a halogen. Okay, so halogen we know has how many valence electrons? If this is a full valence electron shell here, valence shell here, okay, we know that argon has 8. We look over here, okay, that means chlorine has 7. So chlorine needs how many electrons? How many electrons does chlorine want? Okay, it only needs one to fill its valence shell to look like argon. So what's going to happen is chlorine is going to gain one electron. So we know that it's chlorine needs to gain one electron in order to become to fill its valence shell. With the crossover method, boom, boom. Okay, I am left with Al. I'm not going to write a 1 because we know once there is one aluminum, okay, there's always one aluminum. You can't we can't go any more than that. Okay, we can't say, we know that there's one aluminum, so that's it. And then we have chlorine, then has 3. We have 3 chlorine atoms or ions in this ionic compound. Okay, so if you do that crossover method, the crossover method is very simple. You just need to be able to figure out what the ionic charge is for each of these ions. Okay, and again, you can count that based on where they are. Okay, so if you're looking for your cations, most of the time your cations are going to be in group 1, group 2, and group 13. Okay, and then your anions are going to be from group 14 all the way to 17. And you can count backwards if you'd like to as well. 8, 7, 6, 5, 4, 3, 2, 1. Again, skip the transition metals for right now. These are, we're not using these as of yet, okay? But again, 8, 7, 6, 5, 4, 3, 2, 1. Okay, and again, based on where they are in that on the periodic table or what group they're in, they're going to want to lose or gain electrons. Like I said before, is it easier for lithium to gain 7 electrons or lose only 1 electron? Is it easier for sulfur to lose 6 electrons or only gain 2 electrons? And again, remember, electrons are negatively charged. So if I gain an electron, I'm becoming more negative than I was in my neutral, unstable state. Okay, because my ultimate goal is to look like one of these noble gases. Okay, and they're going to look like the noble gas that is closest to them. So lithium is going to want to look like neon. Sodium is going to want to look like argon. Sulfur is going to want to look like argon. Oxygen is going to want to look like neon. Okay, so again, they want to fill up their valence shell. They want to fill up that valence electron configuration so that they can look like these really good looking stable um, elements.